Welcome to this lecture on nested quantifiers. Now, to define this concept, let me use an example of a binary predicate. Say P. So remember, P of xy is a propositional function that when you give it two specific values for x and y, will return a proposition. But as is, this is not a proposition, as you remember, because the values of x and y are not defined. So instead of assigning values to x and y, let's add quantifiers to fix this problem. So for example, we could add a quantifier that exists y in front of pxy. Now notice what this means is that y is now a bound variable since it appears in the scope of this quantifier, whereas x is still a free variable. Therefore, this is not a proposition until and unless we specify the value of x. So let's do that by adding yet another quantifier in front of this expression, namely for all x. Now we have a proposition of predicate logic with two quantifiers. The way you read it from left to right is for all x, there exists y such that p of xy. So let's write this down since it's very important. For every x in the domain of x, there exists at least one y in the domain of y such that p of xy is true. So stated like that, this proposition makes sense. Just realize now that we have a new situation, which is the topic of this lecture, namely we have one quantifier nested inside another. What does that mean? Well, notice I didn't specify the scope of the for all x quantifier here, but if I added the parentheses to show it explicitly, you would right away notice that there exists y is inside the scope of for all x. And that's an example of a nested quantifier. Now I'm going to remove the parentheses because they are not really needed here, and they kind of complicate the proposition. But that is an example of a nested quantifier. Now let's consider a second example of a proposition of predicate logic with nested quantifiers. Instead of taking a completely different one, let's take one that also only has the predicate P. But for this one, we're going to add the quantifiers in the opposite order. So what we would get is the proposition there exists y for all x p of xy. Now let's translate that into English. That's a little bit more intuitive. It says, there exists at least one value of y such that for every possible value of x in its domain, p of xy is true. Now these two propositions are quite similar. They use the same predicates and they use the same quantifiers. So naturally the question we need to ask ourselves is whether these two propositions of predicate logic are logically equivalent. Please stop the video and answer this question on your own. So remember, we can't use truth tables to prove that two propositions are equivalent. One way to do that would be to use equational reasoning. But as it turns out, these two propositions are not equivalent, so all we need to do is to come up with a counterexample. So what's a counterexample? Well, it's a specific domain for x and a specific domain for y and a specific meaning or relationship for p that will make one of these propositions true and the other one false, or vice versa. So here is the counterexample that I came up with. I hope you came up with a different one, or maybe even the same one, but at least I hope you came up with something that works. So let's pick for the domain of x the set of non-negative integers, the natural numbers. And to make it easier, let's pick the same domain for y. So x and y can be any integer from 0 up. And let's pick the relationship denoted by p to be the following. P of xy is true if and only if y is greater than x, or x is less than y. Now, let's consider the meaning of the first proposition. It says, for every integer, there exists an integer that is greater than the first one. Well, clearly that's true. In this particular case, if x is an integer, all we need to do is pick y to be, say, x plus 1, and x plus 1 is always greater than x. So in this particular case, the first proposition in this counterexample is true. Now let's compute the truth value of this second proposition in the same interpretation, in the same example. What it says is that there exists an integer y such that y is strictly greater than every integer. Well, that's clearly not possible. There is no integer that's larger than any other integer, including itself, by the way, because there is no such thing as a largest integer. Therefore, this proposition under the same counterexample is false. So clearly these two propositions are not logically equivalent. And so the conclusion here is that the only difference between these two propositions is the order of their quantifiers. And clearly that order matters for the meaning or the truth value of these propositions. So keep in mind that the way in which quantifiers are nested and the order in which they are nested matters.